Welcome to Paper Simplified, a podcast brought to you by SILMA AI. Today we're diving deep into Attention is All You Need, the paper that introduced the world to the transformer model. This paper single-handedly revolutionized natural language processing.
Yeah, it really shook things up. Before transformers, we were stuck with recurrent neural networks, or RNNs, for handling sequential data like language.
And RNNs, they had this habit of processing text one word at a time, which really slowed them down, especially with longer sentences. It's like trying to understand a story by reading one word at a time. You miss the big picture.
Exactly. The authors of the paper recognized that limitation RNNs really struggled to capture those long-range dependencies, the connections between words that might be far apart.
So that's the problem they set out to solve. Let's unpack how they did that.
So their solution, the transformer, ditched the full sequential processing idea and instead relied solely on this concept called attention.
Okay, I'm intrigued. Tell me more about attention.
Imagine you're reading a sentence. Your brain naturally focuses on certain words that are key to understanding the meaning. That's basically what the transformer's attention mechanism does. It figures out which words are most important to pay attention to, even if they're far apart.
So instead of going word by word, it's looking at the whole sentence at once, figuring out how the words connect.
Exactly. Now let's look at the structure of the model. As shown in Figure 1 of the paper, the transformer is built with an encoder and a decoder.
Okay, just like in other models that transform one sequence into another, like translating languages.
Exactly. The encoder takes the input, like an English sentence, and creates a representation of it. Then the decoder uses that representation to generate the output, maybe a French translation.
So far, so good.
Yeah.
But where does this attention come into play?
Each layer of both the encoder and decoder uses multi-head self-attention, followed by a position-wise feed-forward network.
Multi-head self-attention. That sounds complex. Can you break that down for me?
Think of it like a team of experts analyzing a text. Each expert or head focuses on a different aspect of the language. One might focus on grammatical relationships, another on the overall meaning, another on how words relate across the sentence.
So it's getting a much richer understanding of the text by looking at it from multiple angles simultaneously.
Exactly. This allows the model to grasp nuances and connections that a single attention mechanism might miss.
Okay, I see the power of this approach. But if it's looking at everything at once, how does it keep track of the word order in a sentence?
That's where positional encoding comes in. They cleverly weave in information about word position using sine and cosine functions. It's a math trick that lets the model understand word order without sequential processing.
That's impressive. So by combining multi-head self-attention with this positional encoding, the transformer processes entire sentences, simultaneously making it faster and better at understanding those long-range relationships between words.
Precisely. And the paper goes into detail about how attention is specifically used within the transformer. There are three main ways.
I'm listening. Tell me more.
First, there's encoder-decoder attention. It's the classic attention mechanism found in other models. It helps the decoder link the input to the output during generation.
So the decoder is looking back at the encoded input to figure out what to generate next.
Right. Then you have self-attention within the encoder. This allows each word in the input to look at all the other words and figure out how they relate.
It's like each word is having a conversation with all the other words, trying to understand the bigger picture.
Precisely. And finally, there's masked self-attention in the decoder. This ensures that the decoder can only see the words that come before it when generating the output.
That makes sense. It keeps things flowing naturally, preventing the model from peeking ahead at future words it's supposed to be generating. So we've got this powerful attention mechanism at the heart of the transformer. What else makes it special?
They went a step further and compared self-attention layers to traditional recurrent and convolutional layers. They looked at things like computational complexity parallelization capabilities and their ability to handle those long-range dependencies.
And did self-attention come out on top?
Absolutely. They showed that self-attention is more computationally efficient, especially for shorter sequences like sentences. And of course, it excels in capturing those long-range dependencies, making it perfect for understanding language.
So in theory, the transformer sounds amazing, but how does it perform in practice compared to the older models?
That's where the experimental results come in. They tested the transformer on two machine translation tasks, English to German and English to French, using standard datasets.
And did it live up to the hype?
The results were really impressive. On the English to German task, their transformer model achieved a new state-of-the-art BLEU score.
Hold on. For those who might not be familiar, what's a BLEU score?
It's a way to measure the quality of machine translation. The transformer blew past the scores of all previous models.
So it's not just theoretical, it's producing better translations in real-world scenarios. How about the English to French task?
The transformer aced that one too, outperforming all other models. But here's the kicker. It achieved these amazing results with significantly less training time and resources.
That's incredible. So we're talking about a model that's not only more accurate, but also more efficient. A win-win.
Exactly. But they didn't just test machine translation. They also wanted to see how the transformer would handle a completely different task, English constituency parsing.
Okay, remind me what constituency parsing is all about.
It involves analyzing the grammatical structure of a sentence, breaking it down into its parts. Think of it like diagramming a sentence, but much more complex.
So they wanted to test if the transformer could generalize to other NLP tasks beyond translation. Did it pass the test?
Surprisingly well, actually. It outperformed almost all previous models, which is remarkable considering it wasn't designed for parsing.
That's really interesting. It seems like the transformer can handle a variety of NLP tasks. Let's take a moment to recap before we dive into the finer details. Okay, so we've covered the basics, attention replacing recurrence, the multi-head self-attention mechanism, and how the transformer outperformed other models. Now I'm ready to get into the details of the paper.
Let's do it. Section 3 of the paper, called Model Architecture, gets into the nitty-gritty of how the transformer is structured.
Great. Section 3.1 focuses on encoder and decoder stacks, which we touched on briefly. Can you walk me through how they're structured and how they differ from those in traditional encoder-decoder models?
Sure. The encoder stack has 6 identical layers, each with 2 sublayers. The first is that multi-head self-attention mechanism we talked about.
Right. That's where the model analyzes the relationships between words in the input.
Exactly. The second sublayer is a position-wise feed-forward network. It processes each word's representation individually.
So it's adding another layer of processing to refine the information from the attention mechanism. What about the decoder stack? Is it different from the encoder?
The decoder stack also has 6 identical layers, but each layer has 3 sublayers instead of 2. It's got the multi-head self-attention and the position-wise feed-forward network, just like the encoder. But there's a third sublayer that performs multi-head attention over the output of the encoder stack.
So the decoder is not only looking at the words it's already generated, but also paying attention to the encoded representation of the input. That makes sense for translation.
Yeah.
You need to refer back to the original text.
Exactly. And to ensure the output generation process flows naturally, the self-attention in the decoder is masked. It prevents it from looking ahead at future words.
So it's maintaining that sequential order, even though it's processing everything in parallel. Very clever. Now let's get into the heart of it. Section 3.2 is all about attention. I'm ready to understand how this mechanism actually works.
This is where they explain scaled dot product attention and its multi-head version.
Scaled dot product attention. It sounds complicated.
It's actually quite elegant once you break it down. Think of it this way. Each word in a sentence acts as a query. It's like each word is asking a question.
Okay, each word is curious. What are they curious about?
They're curious about how they relate to the other words in the sentence. The other words act as keys.
So each word is trying to figure out how it connects to the other words. How does it determine which connections are the most important?
That's where the dot product comes in. It calculates how similar the query word is to each of the keywords. The more similar they are, the higher the dot product.
I see. So it's scoring each word based on its relevance to the current word.
Exactly. And then these scores are scaled down and passed through a softmax function to turn them into probabilities.
So each word has a probability score that represents how much attention it should pay to other words.
Precisely. And finally, these probabilities are used to create a weighted average of the values, which contain information about each of the key words.
So the final output is a representation of the current word that incorporates information from all the other words weighted by their relevance. It's like a sophisticated filtering system extracting the most important information.
That's a great way to put it. Now remember the multi-head part of multi-head attention. Instead of one set of queries, keys, and values, the model actually learns multiple sets.
So it's like having multiple experts, each focusing on a different aspect of language, conducting their own attention analysis.
Precisely. Each head calculates its own attention weights and a weighted average of the values. These outputs are then combined to produce a richer representation of the sentence.
Okay, now section 3.2.3 talks about how attention is applied in different ways. We've already touched on encoder-decoder attention, self-attention in the encoder, and masked self-attention in the decoder. Can we talk more about those?
Of course, in encoder-decoder attention, the query words come from the decoder, and the keys and values come from the encoder's output.
So the decoder's asking, given what I've already generated and the meaning of the input, what word should come next?
Exactly. Then with self-attention in the encoder, each word is looking at all the other words in the input, trying to understand its context.
That's how the model captures those long-range dependencies, right?
Yeah.
It's not limited by sequential processing like RNNs.
Precisely. And lastly, masked self-attention in the decoder ensures the model generates words in the correct order, only looking at words that have come before.
Like making sure you read a book in order and don't skip ahead. This attention mechanism is really amazing. Now, what about position-wise feed-forward networks in section 3.3? What do?
After the attention sublayers, each layer in the encoder and decoder has this position-wise feed-forward network. It processes each word's representation individually.
So it's like a final touch to refine the information extracted by the attention mechanism.
Exactly. The transformations in the network are the same for each word, but the parameters are different from layer to layer. This allows the model to learn unique features for each position.
I see. It's adding another layer of depth to the model's understanding of word order and context.
Okay, on to section 3.4, embeddings and softmax. How does the transformer handle converting between words and their numerical representations?
Like many NLP models, the transformer uses learned embeddings to convert input and output tokens into vectors. These are numerical representations of words. So each word has a unique vector that captures its meaning and relationship to other words.
Exactly. These vectors are then processed by the encoder and decoder stacks. Interestingly, they share the same weight matrix between the input and output embedding layers and the pre-softmax linear transformation.
So they're using one set of weights for multiple purposes. That's efficient.
Yes. And that pre-softmax linear transformation is important because it turns the decoder's output into probabilities for each word in the vocabulary. This allows the model to predict the next word.
That's crucial for tasks like translation and text generation. Now let's move on to section 3.5, which covers positional encoding. You mentioned this before, but I'd like to dig a little deeper.
Remember, unlike RNNs, the transformer doesn't inherently understand the order of words in a sentence, so they had to provide that information through positional encoding.
Without it, the model wouldn't know the difference between the cat sat on the mat and the mat sat on the cat.
Right, exactly. Positional encoding makes sure the model knows where each word belongs. They chose to use sine and cosine functions with different frequencies to create these encodings.
Why those functions? That seems like an unusual choice.
They figured using sine and cosine functions would make it easier for the model to learn the relative positions between words. They even experimented with learning positional embeddings, but they found that the sine and cosine approach worked just as well.
So they went with the simpler, more elegant solution. I like that. Now to section 4, why self-attention? Here's where they really make their case for self-attention.
This section justifies why they chose self-attention over recurrent and convolutional layers.
Okay, I'm all ears. Why is self-attention so great?
They highlight three main reasons: computational complexity, parallelizability, and capturing those long-range dependencies.
Let's break those down one by one. Starting with computational complexity, how does self-attention compare to the other approaches?
They found that self-attention layers are more efficient than recurrent layers, especially for shorter sequences like sentences. This makes the transformer faster to train.
A clear speed advantage.
Yeah.
What about parallelization? How does self-attention perform there?
Another win for self-attention, because it uses matrix multiplications which can be easily parallelized. The transformer can be trained much faster than RNNs. It's like having a team of workers instead of just one.
That makes sense. And what about capturing those long-range dependencies? We've talked about this, but I'm curious to hear their arguments.
They show that self-attention is much better at capturing relationships between words that are far apart, which is essential for understanding the nuances of language. RNNs just couldn't do that as well.
So it's not only faster and more efficient, but also better at understanding language. They also mentioned another advantage of self-attention, right?
Yeah.
Something about interpretability.
Yes. They suggest that self-attention could lead to models that are easier to understand because you can actually visualize the attention weights. You can see which parts of the input the model is focusing on, making it more transparent.
That's interesting. It's like you can look inside the model's brain and see how it's thinking. Now on to the training process. Section 5, training, goes into how they train their transformer models.
This section is all about the practical stuff. They train their models on those standard WMT 2014 English, German, and English-French datasets we mentioned earlier, using the Atom Optimizer and a learning rate schedule.
Okay, so standard procedures for training deep learning models. What about preventing overfitting? Did they do anything special?
Yes, they used three types of regularization: residual dropout label smoothing and attention dropout.
Can you remind me what those are and why they're helpful?
Residual dropout randomly drops out connections within the model during training. This makes the model learn more robust representations that aren't too reliant on any single feature.
It's like making sure the model doesn't put all its eggs in one basket. What about label smoothing?
Label smoothing prevents the model from becoming overconfident in its predictions. It might seem counterintuitive, but it leads to better generalization because the model is less likely to be fooled by noisy or unusual data.
It's like teaching the model to be a little more humble, which actually makes it more accurate. What about attention dropout?
Attention dropout is like residual dropout, but it applies the technique to the attention weights. It prevents the model from relying too much on any single attention head, leading to more diverse and robust representations.
Okay, so a multifaceted approach to regularization, making sure the model is well-behaved and generalizes well to new data. Now, the moment of truth, Section 6, results. This is where we see how well the transformer actually performed.
And the results are impressive. They really delivered.
So did the transformer live up to the hype?
On that English to German translation task, their large transformer model got a new state-of-the-art BLEU score. It outperformed all previous models, including those that combine multiple models by a significant margin.
That's a huge accomplishment. It's one thing to have a good idea, but to actually create a model that performs that well is something else. What about the English to French task?
Equally impressive. Their large model for English to French also got a BLEU score that beat all previous single models. And it did it using a lot less training time and computational resources than the previous top model.
That's amazing. Better results with less effort. What more could you ask for?
And remember, they also tested the transformer on English constituency parsing.
Yeah, what happened there?
Even without any specific tuning for that task, their model did better than almost all previous models.
That's really impressive. It shows the transformer is a versatile architecture that works well across different NLP tasks. Now, Section 6.2 goes into some model variations they explored. Can you tell me about those?
They experimented with changing different parts of the model, like the number of attention heads, the dimensions of the keys, and values the overall size of the model, the dropout rate, and the type of positional encoding.
So they were trying to understand how design choices affect performance. Any interesting findings?
They found that both the number of attention heads and the size of the attention keys kind of had a sweet spot. Too few or too many heads or keys that were too small actually hurt performance.
It's all about balance.
Exactly. And as you might expect, larger models generally did better, but dropout was really important to prevent overfitting.
Yeah, that makes sense. Larger models can learn more complex patterns, but they can also overfit. Dropout helps to avoid that.
Right. They also found that replacing their sinusoidal positional encoding with learned positional embeddings didn't really make a difference in performance.
So their intuition about using sine and cosine functions was right. That's great. Now let's wrap up with Section 7, conclusion.
This is where they summarize their findings and suggest some future research directions.
Okay, let's hear it. What are the main takeaways from this groundbreaking paper?
They highlight that the transformer is the first sequence transduction model based entirely on attention. It replaces those recurrent layers you usually see with their new multi-head self-attention mechanism. They also emphasize that the transformer is much faster to train than architectures based on recurrent or convolutional layers, and it achieves new state-of-the-art performance.
That's definitely a game changer for NLP. The introduction of self-attention and the success of the transformer have paved the way for a whole new generation of models. What about future research? What do they suggest?
They're excited about attention-based models and want to apply them to tasks beyond language. They propose extending the transformer to problems that involve different types of input and output, like images, audio, and video.
That's exciting.
Yeah.
It sounds like they believe attention mechanisms could revolutionize other areas of AI, too.
Exactly. They also suggest looking into ways to make attention more efficient for really large inputs and exploring how to make output generation less sequential.
Those are some fascinating research directions. It's clear that this paper has opened up so many possibilities for AI. This has been a great deep dive. We've talked about the architecture, the inner workings of the transformer, its performance on various NLP tasks. I'm curious to hear your overall thoughts on what makes this paper so remarkable and its potential impact. We've really gone deep into the transformer model, its architecture, the innovations, and how it performs. But what are the key takeaways from attention is all you need? What makes it so groundbreaking?
Well, I think the most significant thing is how they replaced recurrence with self-attention. It's a fundamental shift. RNNs were like reading a book one word at a time, but with self-attention, you can take in the whole page at once.
That analogy really captures it and highlights the power of parallel processing. You're not getting bogged down in the individual words anymore.
Exactly. And that parallel processing is what lets the transformer truly understand those long-range dependencies. With RNNs and their sequential nature, they'd often lose track of connections between words that were far apart. The transformer can see those connections no matter the distance.
So it's like the transformer can understand the full complexity of a sentence, even a paragraph, in a way that RNNs just couldn't.
Exactly. And that ability to see the big picture is what allows for more nuanced and accurate natural language processing.
What else stands out to you as particularly innovative?
The multi-head attention mechanism is brilliant. It's like having several experts analyzing the text at the same time, each one focusing on a different aspect of language, the syntax, the semantics, the relationships between words.
So it's creating a richer understanding of the meaning by considering multiple perspectives.
Exactly. And then you have positional encoding. It's a clever way to keep track of word order without losing the benefits of parallel processing. It's as if each word has a specific address within the sentence.
So the model doesn't get confused about the sequence of words, even though it's processing them all at once. We've also talked about how well the transformer performed on machine translation and parsing. What does that tell us about its potential?
The fact that it did so well on two very different tasks shows just how powerful this architecture is. It's not just a tool for one specific job. It's a flexible framework that can be used for a wide range of challenges in natural language processing.
That's an important point. It's not just a better way to translate. It's a whole new way of approaching how we understand and generate language.
Absolutely. And the speed and efficiency gains during training are really significant too. It allows us to create and train larger, more complex models, which opens up so many possibilities for NLP.
So it's a catalyst for innovation leading to new research that wouldn't have been possible before.
Exactly. Attention is all you need wasn't just a research paper, it was a turning point for the whole field of NLP.
We've covered the innovations, the impact, and the elegant solutions in this paper. But if someone's listening, what's the one thing they should remember? What's the core message here?
The transformer, with its use of self-attention, changed how we process language computationally. It's like going from an old calculator to a supercomputer. It's brought us to a whole new level of understanding in how we analyze and create language.
And this goes beyond just research and academia, right? It's affecting how we use technology every day.
Exactly. Think about machine translation chatbots, voice assistants, even search engines. They're all being influenced by the ideas in this paper.
That's amazing. It shows how research can have a real impact on the world.
Absolutely. And we're only just starting to see what we can do with these attention-based models. The future of NLP and maybe even AI as a whole is really exciting.
So if attention really is all you need, what other problems can we solve with this new way of thinking? What are the limits of these attention-based models? That's something for our listeners to think about as we wrap up this deep dive into attention is all you need. Thanks for joining us.